All right, welcome to our first demonstration video. I'm going to record this video a little roughly because I'm just trying to get through my workflow here and figure out how we're going to do these videos for the rest of the course. So I've opened up Mathematica and opened up this notebook, which you too can download, and I sort of encourage you to and play along in your own copy of Mathematica. So we're going to start by defining a graph. So here I am. I've typed graph. This is a list of the vertices, the numbers 1, 2, 3, and 4. And then the cycle graph, I connect vertex 1 to vertex 2, vertex 2 to vertex 3, 3 to 4, and 4 to 1. If you hear clicking in the background, that's my mechanical keyboard. All right, if we hit Shift-Enter, Mathematica will draw the picture for us, and that is indeed the 4-vertex cycle graph. Now, if I go ahead and try the path graph, again, 1 is connected to 2, 2 to 3, and 3 to 4, but I don't connect 4 to 1. That has 4 vertices. And if I try the complete graph, then every vertex is connected to all 3 other vertices. And it makes a drawing. This thing where 2 edges cross over each other is not a vertex because it doesn't have a little circle indicating that it's a vertex. Now actually, the cycle graph, the path graph, and the complete graph are common enough mathematical objects that they're built into Mathematica itself. So for instance, if we want a 12-vertex cycle graph, we type cycle graph 12 or cycle graph 153. If we want a path graph, for some reason I'm not really sure about, you have to use range instead of just typing the number of vertices. But here's a 25-vertex path graph, and here is a 153-vertex path graph, and here's a 7-vertex path graph. Similarly, we can get the complete graph with 6 elements, or 8 elements, or 17 elements, and you see that complete graphs are really beautiful. We'll go back to 4 for the moment and just note that we get a different drawing, but we can tell that every one of the 4 vertices is connected to all 3 others. So actually this is the same graph as this one. Okay, now we can create adjacency matrices in Mathematica as well. So if we go ahead and Shift-Enter here for the path graph, we see that we have 1s on the subdiagonals. This 1 in the row 1, column 2 position means that vertices 1 and 2 are connected by an edge. 2 and 3 are connected by an edge. 3 and 4 are connected by an edge. And of course, symmetrically, since 1 and 2 are connected by an edge, 2 and 1 are also connected by an edge. We can do the same thing for the cycle graph. And for the complete graph, where we see that in the cycle graph, it's like the path graph with the extra edge connecting 4 and 1. And in the complete graph, I've filled in all 6 possible connections between different vertices. Now, we're going to think about the diffusion operator that we defined in the notes. So the first thing to do is write down the degree matrix. Here we're using some Mathematica syntax. The degree matrix is a diagonal matrix whose diagonal elements are given by the list of vertex degrees of vertices in G. Remember that degree of a vertex is just the number of edges which meet there. So for the path graph, the end vertices have 1 edge coming in, they have degree 1, and the middle vertices have degree 2. They have 2 edges coming in. For the complete graph, say with 6 entries, 6 vertices, each vertex is connected to 5 others, so we have a diagonal matrix of 5s. Of course, if we take the complete graph on 4 vertices, we have a diagonal matrix of 3s. Now, we remember that the diffusion operator was the adjacency matrix times the inverse of the degree matrix. So let's just define that. Just as a note, this G underscore means it's a variable. This colon equals is a function definition. And this says diffusion operator of G should be adjacency matrix of G. This dot is matrix times the matrix inverse of the degree matrix of G. So for the cycle graph, we have this diffusion operator. It's just like the adjacency matrix, but with 1/2 instead of 1s. That's because in the cycle graph, remember, every vertex has degree 2. Let's just take a look at the degree matrix of cycle graph 4 in matrix form. So if we were to take the inverse of that matrix, we would see 1/2 down the diagonal. And those are the 1/2. I'm just going to restore that we see scattered around in the diffusion operator. For the path graph, we see some 1/2. These are diffusion from vertices of degree 2, and some 1s. These are diffusion from vertices of degree 1. And of course, in the complete graph, we again get a scaled copy of the adjacency matrix. It's worth thinking about why this is, but I'll let you think about that more as a homework problem. Now we're going to look at the effect of the diffusion operator after taking a lot of steps. So remember that we thought of the diffusion operator either as the diffusion of some substance, like a gas or liquid or something, or as better the diffusion of probability of the location of a walker performing a random walk. So I'm just going to invoke some code that I wrote before. What it does is it plots functions over a graph. So I'm going to plot the function 1, 1, 1, 1 over the path graph with 4 vertices, and you get a picture like this. If I did it over the path graph with 17 vertices, sorry, I need 17 ones, of course. Then you would get this picture. And to plot 25 ones, I'd get this picture. Okay, so I'm now going to come up with a little demonstration. So what we're going to do is we're going to look at the probabilities of being in various locations after a certain number of steps of diffusion. So we're starting with the path graph with 5 vertices, and this says that at time sort of 0, the probability of being in position 3 is 1. We are definitely in position 3. And for technical reasons, I need to show you the plot after one step of diffusion, where there's a 1/2 chance that you move to this vertex and a 1/2 chance you move to this one. Now, let's just see what happens to those probabilities as I continue to take random steps. So after the next step, it looks like this. If you were here, you might have moved here or here. If you were here, you might have moved to this end or back to the middle. Of course, there are two ways to get back to the middle and only one way to get to the end, so we now have more probability of being in the middle and less at each end. I'm just going to continue to step. And you can see this interesting phenomenon that for the path graph, we just get this blinking back and forth between the two possibilities. This is because there's a kind of even-odd phenomenon going here. If you're at vertex 1, 3, or 5, you have to move to an even-numbered vertex 2 or 4. If you're at 2 or 4, you have to move to an odd-numbered vertex 1, 3, or 5. It's this kind of thing which motivates you to consider what's called a lazy random walk, where you either stay put with probability a half or you take a diffusion step. So here is the lazy walk operator. Half the time you stay put, that's the identity matrix. Half the time you diffuse. We'll make the corresponding picture, lazy walk for path graph range 5. All right, this is what it looks like after one step of lazy diffusion. Remember, you started at position 3, and there's a 50% chance you just stayed there. And now you'll note that over time, this seems to be converging. And in fact, it doesn't take all that long before you see a 25% chance at being at each of the middle 3 vertices and a 12.5% chance that you're at one of the end vertices. So we can try this again for the 25-step random walk, where you're starting at vertex 3, so you have these chances after one step of being at a vertex 1, 2, 3, 4, or 5. But again, if I go ahead and look at the evolution of probabilities, you'll see that gradually I have some chance of making it all the way to the other end of the path. And I'm just going to scroll forward now. And you can see that these things, even after 100 steps, still reflect some bias towards your initial position. But if I increase it to, let's say, 1,000 steps, the probabilities are getting reasonably close to converging. You see a probability of twice as much on each of the 23 interior vertices and half that on the 2 boundary vertices. Now let's look at this again for our other graphs. Diffusion on the cycle graph with 4 vertices. Here's what happens when I start. And you can see that again, with raw diffusion, we have the same even-odd problem. But with lazy walk diffusion, it goes very quickly to equally probable in each of the 4 positions. Of course, this will still happen if I take a larger cycle graph. And in fact, it happens faster than it does for the path graph. So by 1,000 steps, at least up to numerical precision, I have the same 4% chance of being in any one of the 25 different locations. Let's look at the complete graph. So here is regular diffusion on the complete graph with 6 vertices. And notice that starting here, you already have an equal chance of being anywhere else, and extremely quickly it converges to equal probabilities of being anywhere on the complete graph. If I do the lazy walk, it converges even faster. So these are the kinds of questions that we're going to be interested in answering about random walks on graphs. Uh, does the limit distribution converge to evenly distributed across the vertices? Apparently, yes for some graphs, no for others. What distribution does it converge to? How fast does it converge to that distribution? Does it converge from any starting position or starting distribution of probability? And how fast does it converge? So you can look at, for instance, the lazy walk on a random graph. Here's a big random graph. It has 30 vertices and 152 edges. You can see that after one step of lazy walk, we started at vertex 3, which is here, and over time, it rather quickly goes to a limiting distribution. Here's a different random graph. Again, rather quickly going to a limiting distribution. And we can try a smaller random graph where we can see better what's going on. Let's say 7 vertices and 18 edges. So in this random graph, you can see it converges to what's not an even distribution of probability, but whatever it is, it's a steady state. All right, download this notebook and try it out yourself.